Let's give a big hands to Nitesh and let us start.
Thank you all, and thank you again to the organizers for inviting me. So I'm not going to use the mic. I'll try and project. If you can't hear me, I'm sorry for you. If you can hear me, I'm happy for you. All right? So let's set that up. And so I'm sort of going to talk about today is thinking about networks and how data and how we can bring together different data elements to help us understand our coastal areas. And especially I'll talk about the issues with invasive species. And the viewpoint that we take in our research is that we are in a complex world, and the complex world is sort of having interacting components. Arup earlier today had this wonderful image of different interaction layers, where you had the social information, the earth layer, etc. And each of those components were interacting with each other. And there was a sequential effect, there was a dependency effect, there was, lead and lag effect, if you may will, and so on. So, and even Arup and I, as he was mentioning earlier as well, have collaborated on networks for climate data sciences too. So what's sort of, the talk today is sort of on our coastal regions. And if you think about is, imagine the global shipping traffic that goes from ships travel from the port and they come together to weave a network of global shipping traffic that sort of helps provides transportation to our goods. We are searching for information online. When we go from one page to another web page, that is a sequential pattern where we start and where we go is dependent on where and how we find the information are related to each other. If you consider the trajectories of vehicles, the shipping movement, the flow of information, the spreading of diseases, and if we take each one of them as a complex world phenomenon, contributing the big data, that sort of helps you visualize their dependencies. As I go from one place to another in a vehicle, as I have stops, there is rerouting that happens. We are weaving a network as a result of that. So, and if you think about a shipping network, where we have here, let's say that I have ships that go from Shanghai to Singapore to Los Angeles, and they are essentially weaving a network. A ship may go from Singapore to Singapore, Singapore to Los Angeles, Shanghai to Singapore, Singapore to Seattle, and so on, Tokyo to Singapore, and so on, and we can build a network that represents this relationship among the ship movement traffic. However, if you think about it, if you just look at this figure, there's something extremely incorrect with this. If I just look at the ship frequency here, based on where the ship came from, the frequency of its distribution, either to Seattle or Los Angeles, is different. And if I build a first order network, which is how network science has been done, where we just assume this first order dependency, we look at Singapore, Shanghai, Singapore, Singapore, Los Angeles, and we build a network connection, and we say, all right, ship goes from Shanghai to Singapore, ship goes from Singapore to Los Angeles, and so on, and we look at that first order relationship and we build a network, but we keep no memory of where the ship originated from. Depending on if the ship came from Shanghai or the ship came from Tokyo, whether it goes to LA or it goes to Seattle are two entirely different things. So how do we begin to create a network representation that takes us from there? So why is it important for us? It's important for us to think about how we build these networks correctly. If I forget about where the ship came from, if you're searching for information, the first web page you go to, and how from there it links you to another web page, that links you to another web page, etc., until you find your information. Where you started from is very important, not just a penultimate page that you find yourself at. Similarly, the same thing applies to shipping traffic as well, where it's not just the first order Markovian relationship among the ports that you go from A to B, I build a network, B to C, I build a network, but I forget I came from A. It's important to consider there's a higher likelihood of ships who go from Singapore to LA if they came from Shanghai, and there's a higher likelihood of ships to go to Seattle if they came from Tokyo. If I don't keep that information in mind, my network is incorrect. It is not representing the actual data. And I can keep building on this network and so on. So essentially what I'm trying to get at is, it is very important to understand this ship movement traffic. And the reason being, if we don't model it correctly, it puts our coastal areas at risk to invasive species. And let's think about how that happens. Let's say a ship load starts from Shanghai or the port of Bombay, right? And the ship says that it doesn't have enough cargo, and to maintain the voyage, to maintain the buoyancy during the voyage, to maintain the stability during the voyage, the ship loads in the water into the ballast. Over here, this is the ballast water. It loads in water from the port and goes on its voyage from Bombay, right? So let's say it goes from Bombay to Singapore, and then in Singapore it loads up the cargo, and then it empties the ballast water in Singapore, and then it goes on to Seattle or Tokyo or wherever the journey may be. Now that sounds perfectly okay to us, that, you know, hey, it's one giant body of ocean, whether it's the Indian Ocean or the Atlantic Ocean or the Pacific Ocean, and the ship is leaving the port of Bombay and going to Singapore. It needs for stability during the voyage. It doesn't have all the cargo, so it's loading up the water from the port. And when it reaches Singapore, it loads up more cargo and empties the water out. Seems logical to do. But what happens is, as it's loading up the ballast water in Bombay, and it discharges the ballast water in Singapore, along with the water, it also discharges organisms that were present in the water at the port of Bombay. Now, those organisms may not be native to the port of Singapore. And now those organisms get injected to the port of Singapore. The native organisms go, hey, what just happened? The invasive organisms go, hey, this ecosystem is very much like the ecosystem of Bombay, only much cleaner. Let's reproduce, right? That's what organisms do. That's the process of natural selection. That's the process of adapting to a new environment. You reproduce. And then those invasive species take over the local port. In the United States alone, the invasive species are $120 billion of annual loss, just caused by the ship movement traffic. So we ask ourselves, so what to say? And essentially it's something which, and it's not just in the ballast, in the hull of the boats, it could be attached on the, where the boats are moving, and the species could move from one port to the other. There's nothing illegal about it. But the corporations have to do something about it. How do we tackle it? And so this invasive species problem is what we need to rescue our coastal areas from. And because of this problem, I argue that the first order network, where we just look at port A to port B connection and don't keep a memory of where that ship came from, is incorrect. Because let's assume that a ship is coming from Bombay to Calcutta, Calcutta to Singapore, right? Bombay to Calcutta poses no risk. Let's assume that for a second. Calcutta to Singapore poses a risk. But if I do, and so Calcutta to Singapore doesn't pose a risk. Let's assume that for a second. Bombay to Singapore poses a risk. If I just build my network using the first order Markovian assumption, where I say Bombay Calcutta is one link, Calcutta Singapore is the another link, and the ship sails from Calcutta to Singapore, I go, oh, there is no risk at all. They are ecosystem-wise, species-wise, no risk. Everything is good. But the ship actually came from Bombay to Calcutta, and the ship may still have some ballast water from Bombay. As a result, organisms from the Bombay port, which may pose a risk to the Singapore port. And if I don't look at that in my network model, I have missed that very important piece of information. So we have to tackle the ballast species, and we have to be able to tackle the higher order network dependencies that exist. So that was the focus of a paper. We published a paper on this topic in Science in 2016, where we sort of developed a new approach to higher order networks from that side. So these are some of the images are not projecting clearly. I apologize for that. But so these are some of the biological invasions that have, and I'm going to focus a little bit more on the statistics of Great Lakes. So the Great Lakes are freshwater lakes in North America. Lake Michigan is 45 minutes away from University of Notre Dame. And there has been a significant influx of zebra mussels, Asian carp, etc. Into the Great Lakes ecosystem in the US. They are freshwater. And the reason that's happened is it's because of a network effect. And so thereon, we have to be able to look at this from a network effect perspective. And so if you look at the spread of the species, so as the shipping network, as the shipping traffic increased in the last 3 decades, the number of non-native species increased at each port. So now these species, as the trade happened, which is a good thing, as the world became flatter, as we all got more connected, as our smartphones and Apple computers started getting shipped from Southeast Asia to North America, the species at the ports found a free ride into North America as well, and established homes in the ecosystem that were not native to them, and the native species went in a shock factor. And we can see that the numbers go significantly high as the trading patterns evolved over time. So, but you would ask that, okay, the Great Lakes these are the Great Lakes, right? And Notre Dame is somewhere here. This is Chicago. Notre Dame is somewhere here. The Lake Michigan is here. So if you look at the Great Lakes, these are the ports. And I think that text isn't clear, so I'll try and read it for you here. So this includes regions of the St. Lawrence Seaway and the Great Lakes of the part of Quebec area. So the question that you may ask is, all right, if the Great Lakes, how much traffic does the Great Lakes get? It's a freshwater inland port. It's not that it's connected. It's not like the port of San Francisco or Baltimore or on the coast, on the Gulf of the U.S. They are inland ports, where the ships, they may come to the seaport and then may travel from the seaport through the river channels onto the Great Lakes. So the shipping network is about, just give you some numbers, is about 0.1% of the global movement traffic is coming to the Great Lakes, 0.1%. And ship movements in Great Lakes comprises of 0.5%. So you would say, all right, so this is at the periphery. How is it connected? How does it impact anything in the Great Lakes? Why are we thinking about the global shipping network traffic for Great Lakes? So if you let's look at it as a network. The average path length, so essentially what we are trying to show is that within about 3 to 4 degrees of connection, the Great Lakes are connected to every other port in the world. So the Kevin Bacon effect of network science holds for Great Lakes as well. So essentially, as ships are coming from different ports in the world, the 0.1% of the traffic is connected to every other port in the world because of the network effect. A ship may leave one port, come to the other port, and navigate itself. So there is a connection that exists to some ports from the Great Lakes. And average path length is 4.67. Average path for random network, just to give you some perspective, is 9.48. And the network within the Great Lakes is highly dense. It is highly dense. So once a region in the Great Lakes is exposed, so are the others over a period of time. So it's a highly dense network. So that's the problem that we're trying to understand and solve here. So the way we are sort of thinking about it is, I'm sorry, the images are not getting projected here. So if you think about how do we begin to solve the problem, right? The example of digital Earth really applies here. You have to think about the transportation network, because if we assume that the movement of species in the world matches the shipping network, we need to get that, right? Second, we need to understand what is the model of ballast discharge. Just because a ship goes from A to B, it's not that a port is, it's a risk. If the ship doesn't discharge the ballast water, it is no risk. Because once I discharge the water I filled in port A at port B, then I'm introducing the species, right? So there is a risk of introduction of species, and then there's a risk of invasion of species, because if the ecosystem is not friendly, the species will not invade. I may introduce any number of species, but if the ecosystem is too harsh for the species, it will not invade. So the risk of introduction and the risk of invasion are two different things, and we have to calculate both. That's why we have to look at the environment and ecoregion data. So we have to be able to first look at what's the vector of the spread, the shipping network. Then we have to look at is the ballast water being discharged? Yes or no? And then we have to look at how hostile or similar the environment or ecoregion is for the species to survive, and then we get the invasive species risk probability. So we go through that by building a species. So we have a master equation that sort of looks at what's the efficiency of the species, what's the ballast discharge, and what's the mortality rate of a species. Because the length of the voyage, how long the voyage is, the harsher climate, or the weather patterns the voyage may go through may kill the species irrespective. So we have to look at the mortality rate as well of the species, and we build a network, and then we sort of create a risk assessment network. So this gives us, the species flow network gives us the introduction risk. The ecosystem environment region gives us the invasion risk. And this is digital Earth in many ways. We are combining our data about the shipping network, about our transportation, with our ecosystem, our environmental data, along with the climate models. So we haven't quite gone to the climate models yet, but if we can get a sense of all of these things together, we are then really tackling the digital Earth problem here. Then we can compute clusters, and we can figure out what ports pose a risk to what ports, and provide something to the policy analysis. Now, one thing that I'd like to really mention here is that as computer scientists or engineers, we love our models. We love to show empirical, we love to establish analytically the goodness of an algorithm. We like to show some guarantees, some convergence properties. We like to build things as engineers. We like to demonstrate that these things are robust. But we can do everything we can about showing the risk of invasion. If the policy people are not in the room with you, it will not go anywhere. Because ultimately, these things, these insights, have to inform a policy about ballast water management, right? So we are sort of building a very interdisciplinary team which involves these policymakers, and they have to be able to visualize, understand these scenarios to go from that perspective. So again, it's a very interdisciplinary effort, and our goal is to truly combine all of these layers of data and build these things. So we had a first paper in KDD on this topic a few years ago, and we celebrated it. We called it data mining for social good, that this is a problem. That this is an interesting problem we have tackled, and we were really excited. However, we realized, like the rest of the communities, we are building networks wrong. We were not capturing the higher order dependencies and the variable order dependencies that exist in this data. We were looking at, we did not capture this. We were just looking at this. We did not capture the higher order dependence, which I've made a point already that is extremely important as you begin to think about. So then the rest of the talk, I will introduce the higher order networks algorithm. I hope you are convinced by now that invasive species is a problem, right? And it's impacting our coastal areas. Great Lakes have been hammered by them. In the US, $120 billion of losses of doing invasive species. And we were looking at it as a shipping network approach. And most of our research, and as well as the other research, assumed the first order network relationship, which apparently may not accurately represent the sequential nature of data. And it's not just in this shipping information. Think about vehicle trajectory. I came from Bombay to Calcutta, then from Calcutta we drove to Kharagpur. On the way we made a tea stop because I wanted tea. And so we basically created all these stops, and it was a sequential pathway where things were conditioned on where I originated from. Right? So all of those any delays that may have happened lead to that effect. When we have a mob together in the times of a disaster, when you want to see how people should go away at the time of a disaster or collect at the time of a disaster. If we build a network of people's movements and we only look at the first order connections, we will miss what happened 2 stops before, and we will miss what happens 2 stops later. When we are searching for information online and we only look for, I go from point A to point B, I don't care about what happened before point A, I will miss the memory. It's a system. The system has a memory. The movements have a memory. How do we tackle those? And that's what we propose to do with a higher order network algorithm. And we're trying to basically do this. And also we assume that in this complex system, there is a variable orders of dependence. If you think about a very complex system, which has multiple components in it, not all components will have the same order of dependency. Some may have 2. I may have to go 2 hops away to explain it. Some may have 3. I may have to go 3 hops away to explain it. So I cannot pre-impose an order on the network because that order may be wrong. I have to discover the right order given the sequential trajectory of data from my network. And that's the problem we're trying to solve. So that's the higher order network algorithm. This is what I said was in science a couple of years ago. And we've been building on the work on this for the last couple of years. So we start with the raw data, which is the sequential data available to us. And then we basically say, oh, right, this is the raw data. This is my sequential data given to me. I believe it should be represented as a network. And then we say, okay, I'll take the raw data, and now I'll start to represent the network for it. Then the question becomes, which nodes should split into higher orders, and which nodes should not? And if I'm splitting some nodes into higher orders, what level of higher order they should be splitting into? And then I do the rewiring of the network, and I develop my algorithm. I develop a higher order network. But to make the life of my PhD student more difficult, I said, hey, we have found an exciting problem. Let's solve it. Now, because as an advisor, you have to be, it's a given rule, you make the life of your PhD student miserable, right? So I told Gian, a brilliant student, Gian, I said, Gian, now, if we develop this, and then we tell people that, hey, now you have to reinvent your clustering, your link prediction, your influence maximization algorithm to work with our data structure, our network representation, it won't work. Can we create a representation that is agnostic to the ultimate analysis that anyone wants to do? Can we build a network that to the community detection algorithm, to the page rank algorithm, to the link prediction algorithm, it doesn't look any different than a regular network. If we do that, and then the other constraint was, can we make sure that it reads all kinds of sequential data? So we have used it on cell phone communication data to look at trajectories of individuals, their location, their placement, etc. We have looked at the shipping network data. We have looked at the taxi traffic data. We have looked at web clickstream data. So it's a general at the beginning. And then, of course, it should not increase us. And then, of course, as computer scientists, computational time and complexity have to be taken care of. The size of the graph has to be taken care of, and all those things which are easy, right? Let's leave it to the, so we said, let's work on those 2 things. So that were the important criteria in building this. So the way sort of it works is we take any sequential data. I'm going to focus on ships because we're thinking about coastal areas. Where I have a ship, and this is the trajectory given to me. Ship this goes from Tokyo, Singapore, LA. Ship 2 goes from Shanghai, Singapore, Seattle, etc. And the data that we have access to all the ship movement from Lloyd's Maritime Insurance Unit. We lease the data from them. So I know what ship, kind of ship, when it left, what port, and where it went to for last several years. We have the data. So we can trace a ship movement quite accurately from the data set that's available to us. So we have the data available, and we can track movements of ships from there on. And so what we then did is we counted. So we think of it as constructing n-grams. So we said, okay, this is the trajectory. Now let's make some n-grams out of this data. And that we counted the subsequences. Singapore, LA happened 60 times. Singapore, Seattle happened 65 times. Shanghai, Singapore, LA happens 30 times, etc. So we built these n-grams and their counts from there on. And then we created some probability distributions where we said, all right, if Singapore is the source node, what's the probability of it going to the target node? So once we had the counts, we created probability distributions of those. And then we kept extending the source nodes. We said, okay, if Shanghai is added to Singapore as a conditional in the pathway, how does my probability distribution change? And then we compared the probability distributions using a KL divergence, and we provide some bounds on that. And when we said, okay, is it significantly different or the other? The point here was we can compute the probability distributions of ship movement from one port to the other port, and then we create an extended set, and we bring in that extended set or a port, and we say, hey, does it help us in bringing in more information and more knowledge from that side? So that's what we did for the ship movement traffic. And then once we did that, then we began to build nodes that look like this, right? So we had, so initially we had single order networks. Shanghai to Singapore was one order. This became a two order network node, Singapore given Shanghai. And we built this thing out, right? And then we rewired the edges where we removed Shanghai to Singapore, and we connected this over here as a conditional probability, and we kept doing that. So we kept rewiring the nodes where the nodes still look like the original network, so they could be used by other algorithms at the tail end for analysis, but we were focused on providing more conditional dependence information at each nodes to get the memory. What we are trying to do is capture the higher order dependence, capture the memory that matters. Not every prior sequence information would be statistically significant. So what we are interested in is capturing the prior sequence information that is statistically significant here. And then what we did is that, we said, okay, let's compare. So the convention first order, the number of nodes and edges stays the same. This is the density, this is the clustering time in 4 minutes, and the ranking time in 1.3 seconds. So now, before we did the higher order network work in Nature Communications, there's a very nice paper by Rosewell et al. Where they showed that they were the first ones, in fact, to show a year before, while we were working on our work, they published a paper. So our initial idea was that we will show first order network is a bad idea once you do higher order, and we were going to look at second order network. While poor Gian was doing the work, this paper comes out that shows second order network is the way to go, first order doesn't work. And then I said, Gian, now let's do even higher order, right? And so he worked on that, but he was rewarded with a very good publication as a result. But so this paper on second order showed that first, and they looked at the traffic movements in the cities, and they showed first order is a bad idea, and they said second order, but they still had the Markovian assumptions in it. So they built a second order Markovian representation of the network. And then they say in the paper it doesn't scale well, etc., but they demonstrated that going to the second order results in more accuracy, more concise representation than the first order. So our work is HON. So as you can see, as I go to the second order, I'm building more dependencies. My number of edges and number of nodes will increase, and their clustering time goes up from 4 minutes to 73 minutes. Ranking time goes to 7.7 seconds. So then we built the higher order network. So we max order 2. So we said, okay, what if we just do within our algorithm, we impose the order of 2, so we can directly compare to this work. So we can say, okay, this is what we are finding, let's compare to this work and look at the computations. And we found this. And the reason that we are so much smaller in the number of edges and the size of the network in general than the fixed second order is because not all nodes will have higher order dependency in it, in the ship movement data. Not all ports may have, if the ship is just going from A to B, A to B, A to B, there is no second order, right? So there are certain ports that will only have one order. So in doing so, because in our algorithm, we don't make an assumption on how many orders exist. The max was order 2, and the algorithm said, hey, there is no more than one first order in this, let's stop, or if it's 2 order, let's go on. And then we were able to go up to maximum order of 5, and as you can see, the size of the node, network and edges doesn't increase too much. The clustering time, yes, it's still more than the first order network because it's much more dense, etc. as well here. It's still, it's some order of time, but we can easily scale it, parallelize, distribute this. PageRank algorithm goes this way. But the key point is the size doesn't increase much from a scalability perspective. But yet we were not happy with this result, right? So after we published this, we celebrated this graph at the time of publication, but then we knew that can we make it more scalable, right? Because the search of the actual dependencies and everything else was leading to a large search space. Whereas the actual dependencies were in this triangle, the actual search space was very wide, because we were exploring every possible dependency that could exist in the data. So this paper now, which is under review now in KDD, which is an improved version of this algorithm, and along with that we show that we are able to identify anomalies which are missed by any first order network, right? Where we took other anomaly detection or change point in network detection algorithms that have been working on networks, and we show that if anything happens as a higher order, they are completely missed because an adversary is masking an action and knows how the network is constructed, where you are and is fooling the system from that perspective. So we were able to basically establish a bound on this and show that if we can sort of say that you're going to beat this score, only then. So the way we sort of tackle the problem to where we reduce the order of raw data size to a much smaller search space by pre-imposing a stopping criterion. So we sort of pre-pruned and said, okay, if you don't meet the scale divergence criterion and you don't beat this distribution, you will not, higher order will not make a difference. There is no point searching. So again, so with the higher order networks, existing approaches either ignore higher orders or they modify existing algorithms, which is great as well. So we are not the first ones to identify higher orders. There have been others who have looked at higher orders, but they are focused on the application they were working on. Or they are higher orders, I'll develop a clustering algorithm for higher order and I'll go on my way. What we are trying to come up with is building a network representation which has higher order embedded in it. So it allows us to generalize to all kinds of techniques and methods. So, okay, so this once Jian Xu did this work, his dissertation was done very much on time, and he's off to applying this thinking to picking hedge fund portfolios now, right? At Citadel. So the application, again, let's go back to the invasive species and see some of the results on a global shipping network. So again, we go back to, this is a first order network representation. This is a second order network representation, where now I have introduced a memory where if I come from Tokyo to Singapore, I'm more likely to go to Seattle. If I come from Shanghai to Singapore, I'm more likely to go to LA. So I've created that dependent structure within my network now. And then, so we then constructed both the first order and the higher order network, and then we clustered all the ports of the world. What this graph shows is different colors indicate how different clusters of the world are and where the ports are. All in the red belong to one port based on their movement traffic. All in the blue belong to one port, etc. Now, as a case study, I'd like you to focus on Valletta and Malta Freeport in Europe. Valletta is a very small inland port. It gets maybe one or two ports that connect to it. And Malta Freeport is a big port where a lot of ships come and converge from different areas of the world. They come to the Malta Freeport. What I'd like to point out here is it is erroneous for us to think that Valletta and Malta Freeport belong to the same cluster, because these clusters are signifying shipping traffic. The reason they belong to the same cluster is because we're using the first order network dependence on them, right? Malta goes to the ports in that region. Malta, Valletta is connected to, so is Malta. They are similar, and they must be in the one cluster. But we are ignoring that Malta also gets ships from various other ports in the world. And when we do the higher order network, what we show is Malta actually, now the clustering changes significantly. There are ports even in India that belong to multiple clusters. The Malta Freeport is actually belonging to 5 different clusters. And the Valletta is only connected to 2 clusters only within that inland Europe. Not having this knowledge will not allow us to understand where the invasive species are posing a risk to this region in Europe. Because the risk is not coming from Malta to Valletta. The risk is coming from the other clusters, the yellow, green, and red clusters that Malta is connected to as well. So any modeling that I want to do, I have to take that higher order into mind from that perspective. Now this is another work that's in progress right now. This paper should be going out for review process soon. It went for a review process. You always start with science. When science rejects you, then you think, what do you do now, right? So now the other one was accepted in science, but this one was rejected, desk reject, even better, right? So now we are revamping the paper to get to Nature or PNAS. But the point here is that this is the projections that climate modelers and scientists, friends make, that melting Arctic ice would look like this in 2039. Now all this blue water, what that's going to do is open up shipping pathways. A lot of shipping pathways that don't exist in the Arctic region will now become possible. Even now they're opening up. And the reason, this is an interesting problem, right? The ships burn the worst possible fuel. Like after you take out all the good fuel for cars and everything else, whatever bad fuel is left, we give it to our ships, right? And then they burn, and they create these local climatic effects as a result of that as well. So now, we burn less bad fuel if there's a shorter path that may exist via the Arctic. That's a good point. However, when we may do that, Arctic is a pristine region which has not been connected to the other ports in the world. Are we now risking injecting invasive species in the Arctic and messing up the ecosystem? And we have a great opportunity actually as scientists to understand what's going to happen, what's going on. We can sample the water. So right now we are working with a Canadian scientist who go to the Arctic region and they sample water, and we are seeing what species exist or not exist from that perspective. In fact, I should also tell you the way we are doing species sampling is, we go to a port, there's a special paper that exists, we pour the water from that port on that paper, we dry it off, we carry that paper back to the US, we run it through the sequencing machine, and it can tell us what species actually exist in that port. It's that simple now. It's called eDNA. So getting the DNA of species that exist, of course, in a port of Bombay, where there's a million odd type of species that may be existing, God knows what, right? Could be a problem, right? But of course, and these species have to be documented because they're looking up to a table. So what we looked at is, what is the pathways, introduction pathways to the Arctic from different ports in the world, and we created these networks. And then we created, because we have the shipping network data, we simulated, as Arup likes to call wargaming, we were wargaming, that what happens with this thing, with the species flow, what's the influence per trip, what's the subsequences, what's the rule extraction, etc. So we went through the exercise of projecting what the things could be from a global shipping network perspective using higher order networks for the Arctic region. And we found some of these ports where how Russia, Iceland, Norway, Alaska, Greenland, and how different ports in the Arctic region have influence either from Norway. Greenland and Alaska were fairly isolated, but Norway, Russia, and Iceland pose a very strong codependence risk to the Arctic ports that have been untouched in terms of the shipping traffic and movements, which may not have been found otherwise. So again, so the point here is that we started thinking about higher order networks only because we faced an exciting application, a challenge that our ecologist friends presented to us about invasive species. We looked at it from a higher order. We realized that the first order network was insufficient. It didn't capture the data accurately. We can network our digital Earth. We can digitize our Earth. We can collect all the data. But if we fail to represent it accurately, then we really don't have the truth. Because the network representation that we have, if it misrepresents the underlying data, any analysis is not going to make it correct. So that's what we focused on then, and we have demonstrated it through different empirical studies now on the utility of the higher order network from there on. And something else that we have developed is a wonderful visualization interface where you can actually do war games. You can look at different ports in the world. You can select them. You can say how ship movements are going to change. You can look at the dynamics. So it allows you to visualize and understand the impact of this. So this is also published in IEEE Transactions on Visualization now. And the reason that we did the visualization work was there are ways to visualize networks, but they are mostly restricted to first orders. And we wanted to really allow geospatial, temporal dynamics into our visualization construct. And that's what this is doing. It's allowing us to focus, visualize, and again, the visuals are not looking good over here. And you can download everything that I've talked about today from higherordernetwork.com, right? Where you can our entire source code is open source. The visualization software will be posted as open source again very soon, and you can download that, and the papers are available. Let us know of questions. In fact, the code is also on GitHub, so you can play with it. And to end, I would say it is a networked digital earth. It's a small, small, flat world. The regions are connected and closer in variables than we think. It is not just location and time anymore, right? They are cultural, they are geographical, they are social distances that matters. And in fact, the figure that Arup had in the beginning, I'm a fan of that figure when I saw it, because it truly captures how small the world is. And as we add or multiply the distances across the different layers, it's only going to shrink even more. My action here has an effect in an action on someone. The butterfly effect is actually true, given the world that we are in. Thank you very much. These are the funding agencies, and I can take questions.